AP Calculus ABBC Exam Review Differential Calculus Fundamentals Question 4 Comparing Features of Functions. So we're going to examine end behavior, x-intercept comparison, minimum comparison, and even or oddness comparison in this particular question. F is a function defined on all real numbers, okay? And its formula is given below. So f of x is equivalent to x squared over 4 plus 1. And note that real numbers include numbers like 1, 15.8, um, 0.3, let's say negative 0.3, or even a fraction like 3/5. So basically, numbers that are positive, negative, large or small, whole numbers, or decimal numbers, these are all real. The only thing that real numbers don't include is anything that includes I, which is defined as the square root of -1. This would be imaginary, therefore it's not real. Okay? So g is a function defined on all real numbers, which we just briefly covered, the meaning of real numbers. Its graph, when between -4 and x is 4, is given below. So this is, and the less than or equal to sign as means inclusive, the -4 and the 4 values are included. And we're going to suppose that the trend suggested by the graph's edges continues on forever, so it just continues increasing among the infinite domain of x values, okay? So which of the features are shared by f of x and the function g of x? So we're going to select all that apply. Do they have the same end behavior? Do they share x-intercepts? Do they have the same minimum value? Or and are they both even? So whenever we're discussing end behavior, that's what we're going to compare now. We're thinking about what a graph will do as its domain approaches both positive infinity and negative infinity. And when I say domain, I just mean the x values along the x-axis. So let's look at the domain for f of x as it approaches both negative infinity and positive infinity. Okay, so we want to know what the ends of the graph will look like basically as the graph travels towards negative infinity and positive infinity along the domain or along the x-axis. So here that we can see that the graph continuously increases towards positive infinity and also over here towards negative infinity. think the negative sign is written behind. I'm not really sure, but you get the point. So now we know that the graph is increasing continuously, both in the direction of negative infinity and positive infinity. Actually, it's written in the front. Now, what about g of x? So for g of x, as the domain approaches negative infinity, we see that the graph continuously increases on the left-hand side. And as the domain approaches positive infinity, to the right, we see that the graph also continuously increases infinitely, okay? And earlier, a stipulation was that you can assume that the end behavior of g of x is going to continue in the same fashion. So it's okay to make the assumption for g of x that both extremes will continue infinitely in the positive upward y direction. Therefore, both graphs have the same end behavior. So that option is also correct. Now let's determine whether or not functions f of x and g of x have the same x-intercepts. So a visual inspection of g of x shows us that the x-intercepts occur at -2 and 2. Now let's take a look at f of x. So let's first think about the geometric figure formed by the function. This is not a plot of f of x, rather it's x squared, but we see that when we have the function x to the second power, or x squared, the x-intercept occurs at 0. But now let's take a look at our function, which is f of x is equivalent to 1/4 x squared plus 1, or x over 4 plus 1. So again, this is x squared having an x-intercept at 0, but when we multiply the function by 1/4, this expands it. Some people think that it will compress it, make it skinnier. It actually flattens it out. And by adding 1, we shift the parabola up by a unit of 1. So this is the x and y-intercept now. So this function will always have a value that's greater than 0. Therefore, it will never cross the x-intercept, because in order for a function to have an x-intercept, the outcome of f of x, or the y value, has to be equivalent to 0. Okay? And that's not going to happen here. So there's no y-intercept for f of x, and there are two y-intercepts that occur at -2 and 2 for g of x. Therefore, these two functions don't have the same y-intercepts. Now let's do a comparison of the minimum values of the functions g of x and f of x. A simple visual inspection of g of x shows that the minimum value occurs at 0. Not once, but twice. And whenever we're discussing minimum values, we're talking about the f of x values along the vertical axis, also known as the dependent variables, or more commonly, the y values. So our independent variable, or our inputs, would be the entire domain of g of x, that is all the x values, and our output, where we would choose our minimum value from, would be at some particular y value or f of x value, or again, a dependent variable value. So minimums as well as maximums are always said to occur at some specific y value or dependent variable or f of x value. Now let's think about the minimum value of f of x. So this is our function that I shared with you earlier on. F of x equals x squared over 4 plus 1. And in order to do a simple visual inspection to determine the minimum value of f of x, let's also plot it. So here goes a simple plot. And again, we expect a parabola because of the x squared, but it's a flattened or widened parabola rather than compressed. It's made flatter because we're multiplying everything by 1/4. And then we have a vertical shift of +1, okay? So this y-intercept is actually where our minimum value is going to occur, and we see that right here. So the minimum value for f of x is 1, and the minimum value of g of x is 0. Therefore, f of x and g of x do not have the same minimum values, so we can eliminate this answer option. So let's start by checking symmetry. We'll start off with the function f. F of x is a polynomial given by the function that we were provided with early on. So f of x is equivalent to x squared over 4 plus 1. Now we can express this in an alternative fashion in order to determine whether or not the function is even by examining all of its powers, that is, its exponential powers. So this is equivalent to 1/4 times x to the second power, okay, plus 1 times x to the 0 power. And we know that any variable or number expressed to the 0 power is just going to be equivalent to 1. But the thing that we want to take note of is the exponent 2 and the exponent 0. These are both even powers, and the rule of thumb is that whenever you have even powers, you have an even function. But if you're not satisfied with using this rule alone, you could check and ascertain that f of negative x is equal to f of x. So let's say you plugged in 4. 4 squared is going to give you, let's say 16 divided by 4 is going to give you 4, plus 1, the answer is 5, okay? If you were to plug in -4, -4 squared gives you 16 divided by 4, that'll give you 4. Again, plus 1 will also give you 5. So this is an even symmetric function. Okay. Now let's determine whether the function g is symmetric or not. Since we are not given an actual equation, a function as we were for f of x, we'll have to do a visual inspection. And a visual inspection shows that g of negative x is equivalent to g of x. So we'll just highlight a few examples. So we see here that g of -2 and g of 2 is equivalent to 0, the x-intercept. G of -1 and g of 1 is equivalent to approximately like 3/4. Let's see, g of 3 and g of -3 is equivalent to 2, okay? And it's a visual inspection also shows that this function is symmetric about the y-axis. So if a function is symmetric about the y-axis, it's automatically even, okay? Finally, the shared features of f of x and g of x are their end behavior, so option 1, as well as the fact that they're also both even functions. So these are the two shared features. So option 1 or option 4 or A and D, however you best think about the answer choices. All right.